For decades, rockets were built to be used once. A launch meant millions, sometimes billions of dollars of hardware falling into the ocean, never to be recovered. NASA's mighty Saturn V, which carried astronauts to the moon, cost about $185 million per launch in the late 1960s, over $1.5 billion in today's money, and none of its stages were reused. When the space shuttle was introduced, it promised reusability. On paper, its turnaround time was supposed to be 2 weeks. In practice, the reality was much slower. Each orbiter required months of inspection and refurbishment, often running into millions of man-hours and costing around $450 million per launch. The shuttle was a marvel, but not a fast or cost-efficient one. So when SpaceX announced plans for a rocket that could not only land but fly again within weeks, the industry's reaction was disbelief. Critics said it was impossible. The idea of a 23-story booster falling back from the edge of space and landing vertically was dismissed as science fiction. But the story changed on December 21st, 2015. That night, a Falcon 9 booster returned from orbit and landed safely at Cape Canaveral. It was the first orbital-class rocket ever recovered intact. Then, in March 2017, SpaceX launched and landed the same booster again. For the first time in history, a rocket had completed a true reflight. That breakthrough paved the way for what came next, not just reusability, but speed. By 2018, SpaceX had achieved a turnaround of 71 days between flights of the same booster. In 2020, they cut that to 51 days. By 2021, it dropped to 27 days. And today, the record stands at just 21 days between launches of the same Falcon 9 first stage. To put that into perspective, the shuttle's fastest turnaround was 54 days, achieved only once under immense pressure. Falcon 9 now does it routinely, at less than half the time. The public perception once was that rockets were fragile, complex, and irrecoverable. Today, Falcon 9 boosters are more like aircraft. Land, refuel, check critical systems, and fly again. But what makes this possible? The answer isn't magic, it's engineering. It's physics, iteration, and a design philosophy built for speed. And the deeper we look, the clearer it becomes why Falcon 9 can be turned around so quickly. To understand how Falcon 9 achieves such fast turnarounds, we need to break down the core physics of its return and recovery. When the first stage separates, it's moving at nearly 8,000 kilometers per hour, almost 7 times the speed of sound. A booster this size, 70 meters tall, weighing over 400 tons at liftoff, has to slow down, reorient itself, and guide back to a precise landing pad. Every maneuver is calculated to minimize stress on the hardware and reduce post-flight maintenance. The first principle is thrust vectoring. Each Merlin engine can gimbal or swivel a few degrees, allowing the booster to adjust its attitude in flight. This gives precise control during ascent and descent. The engines aren't just about raw power, they're also the steering system.
The second principle is aerodynamic braking. As the booster re-enters the atmosphere, it uses its bulk to create drag, shedding speed naturally before using precious fuel. SpaceX engineers optimized the rocket's shape to take advantage of this deceleration, reducing the thermal and mechanical loads on critical components. But the real elegance comes from the gravity turn. Instead of finding gravity, Falcon 9 leans with it. On ascent, the rocket gradually tilts eastward, letting Earth's pull curve its trajectory. This means less fuel burned for guidance, and more importantly, it sets up a natural arc for the return trip. By the time separation occurs, the booster is already aligned for a glide back. It's simple, efficient, and saves wear on the engines. Now comes the re-entry. The booster performs a re-entry burn, typically with 3 engines, for around 20 to 30 seconds. This slows it by a few thousand kilometers per hour and shields it from the most intense heat of atmospheric friction. Then, as it descends, titanium grid fins deploy to fine-tune its trajectory. Finally, the landing sequence begins. The booster reignites a single Merlin engine for the landing burn, throttling down to just 40% of its capacity. From there, Falcon 9 reduces its velocity from several hundred kilometers per hour to just 2 meters per second at touchdown. That's slower than a human jog. Think of it as a controlled fall, but one calculated with extraordinary precision. The booster, a skyscraper-sized cylinder, lands softly enough that its legs absorb most of the impact without significant stress to the structure.
This entire sequence is designed not just to recover the rocket, but to recover it in a condition that requires minimal refurbishment. The landing isn't dramatic, it's deliberate. Every maneuver from the gravity turn to the landing burn is optimized to limit damage, thermal stress, and vibration. And this is the critical link to turnaround speed. If a booster came back scorched or battered, it would require weeks of inspection and repair. Instead, Falcon 9 often needs little more than a cleaning, data review, and standard system checks before being rolled back to the pad. The booster isn't rebuilt after each flight, it's inspected like an aircraft. That difference is what enables SpaceX to reuse rockets again and again, cutting weeks or months down to just days. The core physics, thrust vectoring, aerodynamic braking, gravity turns, and propulsive landings aren't flashy. They're fundamental principles applied elegantly. Together, they make reusability practical, repeatable, and fast. And that foundation of physics leads directly into the next piece of the puzzle: iteration, testing, and data-driven design. Without those, physics alone wouldn't be enough to achieve a 21-day turnaround. Physics provides the foundation, but physics alone doesn't explain why Falcon 9 can fly again in just weeks. The real key lies in SpaceX's approach: relentless iteration, rapid prototyping, and data-driven design. When SpaceX first began experimenting with vertical landing, the aerospace community doubted it would work. In 2012, they introduced Grasshopper, a small test rocket built from a Falcon 9 first stage and a single Merlin engine. Grasshopper performed short hops, rising a few hundred meters, hovering and landing back on its pad. Each test looked simple, but it carried massive significance. Engineers were learning how the rocket responded to winds, how quickly the engines could throttle, how precisely the grid fins could steer, and how the landing legs absorbed impact. Every trial produced reams of flight data. Between 2012 and 2013, Grasshopper completed 8 test flights. Some were successful, others ended in abrupt crashes, but none were considered failures. SpaceX treated them as experiments, each one adding knowledge about stability, control, and reusability. By 2014, Grasshopper evolved into the F9R Dev 1, a larger prototype capable of flying several kilometers high. Again, not every attempt was flawless. Some ended in explosions, but every failure was dissected, logged, and applied to the next iteration. This philosophy, testing early, failing often, and learning quickly, became SpaceX's secret sauce. Instead of waiting for a perfect design, they built, tested, and improved in real time. When Falcon 9 began attempting real landings in 2015, the foundation was already solid. The first 2 attempts on drone ships in the Atlantic ended in spectacular crashes. One booster tipped over, another exploded on impact, but by the 3rd try, the lessons from Grasshopper and F9R came together and Falcon 9 landed successfully on solid ground at Cape Canaveral. Since then, SpaceX has refined recovery through hundreds of landings. Every booster is packed with sensors, gyroscopes, accelerometers, and pressure gauges. They feed data continuously to mission control, logging thousands of variables per second. This isn't just for the landing, it's the backbone of rapid turnaround. After each mission, engineers don't need to strip the rocket down blindly. They know exactly which stresses the vehicle endured, which engines ran hot, which areas experienced vibration, which valves need closer inspection. Instead of spending months guessing where potential problems might lie, inspections are targeted and efficient. This is why boosters can be cleared for reflight in weeks, not years. And here's an important detail. The control systems are not driven by complex artificial intelligence. SpaceX relies on robust, predictable feedback loops. If the booster tilts half a degree, the engines adjust. If wind pushes it sideways, the grid fins compensate. Simple inputs, fast responses, reliable outcomes. This approach avoids unpredictability. It also makes inspection easier. Because the systems operate within well-understood limits, engineers know what to expect and how to verify it. The results are astonishing. Some Falcon 9 boosters have now flown 20 or more missions each. In fact, booster 1060, first launched in 2020, has completed over 20 successful flights. That kind of endurance would have been unthinkable just a decade ago. Each reflight validates the design further, proving the hardware can withstand repeated stress with minimal refurbishment. The data doesn't just enable quick turnaround, it improves confidence that the rocket can keep flying safely.
So the secret sauce isn't magic or luck. It's iteration, testing, and data. Grasshopper laid the foundation, crashes taught the lessons, feedback loops provided stability, sensors delivered precision. Together, they created a rocket that could land, relaunch, and break turnaround records. But iteration alone isn't enough. To achieve turnaround times measured in weeks, not months, SpaceX had to simplify the rocket itself. That leads us into the next piece of the puzzle, the elegant engineering solutions that make Falcon 9 reliable, efficient, and quick to fly again. Iteration and data provide insight, but the real speed of Falcon 9 turnaround comes from engineering choices designed for reusability from day one. SpaceX didn't just aim for a rocket that could land, it had to land repeatedly with minimal refurbishment. Take the grid fins. These are 4 cross-shaped panels near the top of the booster. Made from titanium, each fin weighs around 80 kilograms. They deploy after stage separation and provide aerodynamic control during descent. The fins steer the booster precisely, even at supersonic speeds, correcting trajectory in real time. Unlike hydraulic or moving parts systems, grid fins are extremely durable. They rarely need maintenance, which cuts down the time between flights. Next, the landing legs. At first glance, they might look like simple supports. In reality, they are highly engineered shock absorbers. Each leg spreads impact forces across the booster structure, keeping it upright and protecting critical components. The design minimizes the risk of structural damage and reduces post-flight inspection time. They fold up during flight to save space and deploy in a fraction of a second before touchdown.
The Merlin engines are another cornerstone of reusability. Each booster has 9 of them, capable of throttling down to 40% of maximum thrust. These engines can restart multiple times in a single mission, which is crucial for the re-entry burn and the final landing burn. The ability to reliably restart engines reduces the risk of damage on landing, allowing the booster to be prepped for the next flight quickly. Even the booster's structure is optimized for rapid reuse. Components like the interstage, composite fairings, and avionics are designed for minimal wear during flight. Thermal shielding and engine nozzles are made to withstand repeated heat cycles, reducing the need for replacement. It's also worth noting the precision of booster recovery. Landing pads are carefully positioned, whether on the drone ship Of Course I Still Love You or on land. Boosters consistently land within a few meters of the target. This predictability means less cleanup, fewer surprises, and a faster inspection workflow. The results speak for themselves. In 2021, Falcon 9 completed 31 reflights, including one booster achieving 5 launches in a single year. By 2022, turnaround between flights dropped to as little as 21 days, setting records previously thought unattainable. All of these design elements, grid fins, landing legs, engine reliability, and structural durability combine to make Falcon 9 not just reusable, but quickly reusable. SpaceX didn't just recover rockets, it engineered them to be operational again in record time.
These engineering solutions also have broader implications. Faster turnaround reduces costs, increases launch frequency, and opens opportunities for new missions. From Starlink satellite deployment to commercial launches for governments and private companies, rapid reusability allows multiple launches per month with fewer rockets, cutting the cost per kilogram of payload to orbit. And the story doesn't end with Falcon 9. SpaceX is now developing Starship, designed for full reusability, both the booster and spacecraft. The lessons learned from Falcon 9, efficient design, robust feedback loops, and rapid inspection will be applied to Starship, potentially reducing turnaround times even further and enabling a launch cadence that could reach daily flights in the near future. Even today, Falcon 9's record-breaking turnaround is a clear demonstration. With careful engineering, what once seemed impossible is now routine. Rockets no longer have to be discarded after a single use. They can fly, land, and fly again, changing the economics and logistics of spaceflight forever. And if you want to understand the limits of this technology in more extreme missions, check out our blog. What are the challenges of using Falcon 9's reusable technology for deep space missions? The link is in the description. Falcon 9's rapid reuse isn't just a technological milestone, it's reshaping the economics and accessibility of space. Before reusability, sending 1 kilogram to orbit cost around $18,000. Today, thanks to Falcon 9, that cost has dropped to roughly $2,600 per kilogram. That's an order of magnitude reduction, making space accessible to private companies, universities, and even smaller nations.
By reducing cost and increasing launch cadence, Falcon 9 is democratizing space. Startups, international partners, and private research teams can now plan missions that would have been unaffordable just a decade ago. Faster turnaround doesn't just save time, it enables entirely new business models, new science, and new exploration opportunities. The 21-day turnaround record is more than a number. It is proof that humanity is entering a new era of spaceflight. Rigid, expensive, and disposable rockets are giving way to reusable, reliable, and rapidly reusable systems. The future of space is not in scarcity, it is in frequency, accessibility, and iterative improvement. Even with these achievements, challenges remain. Deep space missions, such as crewed Mars flights or long-duration lunar operations, push reusable technology to extremes. Fuel loads, radiation, and thermal stress all increase exponentially with distance. To explore this in detail, we've published a blog. What are the challenges of using Falcon 9's reusable technology for deep space missions? Check the link in the description to explore these engineering frontiers. Ultimately, Falcon 9 shows that great engineering often hides its brilliance in simplicity. A 549-ton rocket returning from orbit might look effortless, but it's the product of meticulous planning, robust testing, and precise execution. That same approach will power humanity's next steps in space. If you've enjoyed this deep dive into Falcon 9's turnaround record, here's how you can stay connected. Subscribe to the channel, like this video, and share it with anyone interested in spaceflight. Follow us on Facebook for updates, behind-the-scenes insights, and more detailed discussions about reusable rocket technology. The Falcon 9 turnaround record is not just history, it's a promise of the future. Faster, cheaper, and more frequent access to space is here. And with Starship on the horizon, that future is only getting closer. As we watch boosters land with precision and take off again in record time, remember this: the impossible only looks impossible until someone designs a solution simple enough to make it routine. Falcon 9 has done that, and it's just the beginning.